Okay. Well, to begin, I want to say that my English and my pronunciation is not very good, so I try to explain it well. Okay. I want to tell you about this idea.
Can you use white chalk? Can you use white chalk? White chalk?
Yeah. But
it's hard to see.
Okay. During the previous lectures, I will have studied these ideas over Cartesian algebra. C, where R is a pure ring and C is a Cartesian algebra. We show that these ideas exist, and if we take idea A R and T a positive number, then we define the Cartesian subalgebra. We take the sum, the home to where this denotes the sin function. And today I want to tell you about these ideas of an ideal A. That is a specific case of this. So we define this idea to be the unit of smallest non-zero ideal J contained in R, such that the phi of the probability morphism that A to the T times Q minus 1 times J is contained in J. This for E and for V in V. When A is the ring R, we have that the test ideal of A is the test ideal. And in the other hand, we can have an explicit description of the test ideals based on the following theorem. Let's see test element. Then the test ideal E. Okay, so we can write the test ideas of the sum of over E and over P of this. Where P runs over all elements. And now we have a list of some properties of the test idea that follow immediately of the this theorem and the definition. We have S and T are real positive numbers. If S is greater than T, then we have the test idea of A to the S is contained in the test idea of A to the T, to the T. Also if also we have the test idea of the A to the M to the T is equal to the test idea of A to the N times T. For M natural number. And 2, there exists epsilon positive that the test ideal of a to the t is equal to the test ideal of a to the t plus epsilon. In other words, it says that the test ideal is constant in a very small interval to the right. 3 for any multiplicative system. W we have the W of the test ideal is equal to the test ideal to the WR and WH. It says that the test ideas commute with localization. Now we define the F-jumper numbers. A positive real number, lambda, is called a jumper number. If the test ideal of a to the lambda is different to the test ideal of a to the lambda minus epsilon. These for R positive epsilon. And if R is irregular, then the smallest test idea is called the effective threshold. Okay. We can see that this idea that corresponding that if t is equal to 0, t is to 0, then this idea is trivial. And the second point here says that is trivial in a smallest interval near zero. So it's trivial for all positive values for t. So we can define the effective threshold that we denote by FPT of idea A hold to the supreme of uh, our t real numbers such that the test idea of A to the t is equal to R.
Lorena, I'm sorry. In your definition, the truth threshold is the smallest test idea or the smallest that you're being number?
The smallest jumper number.
Okay.
Sorry. Okay. Over a ring of characteristics zero, we can define the multiplier ideas and the jumper numbers. So it's worth mentioning that the test ideas and the F jumper numbers were introduced for positive characteristic analogously of these test ideas of these multiplier ideas and the jumper numbers. For this reason, we can see that the test ideas and multiplier ideas share main properties. In characteristic zero, we have the jumping numbers and the multiplier, the jumping numbers are a set rational and discreteness because in positive characteristic, this is more delicate or is not trivial. However, both properties, the rationality have been proved for an arbitrary idea is a regular ring. And for principal ideas, in any F-finite ring. In regular rings. And we have other properties. Well, that R is a ring, A and B are ideas contained in R. Mm. We take S and T rational numbers. So if A is contained in B, then the test ideal of A is contained in the test ideal of B. Furthermore, if A is a reduction of B, it says B is contained in the integral closure of A. Okay.
Is that the definition of reduction?
Reduction.
So you're writing down the definition of it.
This is the B is contained in the integral closure of
Yeah.
A. Okay.
That's the definition, or?
Yeah, that's the
Okay.
definition.
Circular? Well, yeah, I think so, because I think the reduction is that they have to have the same integral closure. So if A is containing B, the zero inclusions, I think so.
So the test idea of A to the T is equal to the test idea of B to the T. Two, we have the A times the test idea of B to the S is contained in the test idea of A times B to the S. And we have an equality. A is principal. And in particular, we have the A is contained in the tensile gear. The last is named the scholar figure. And say that if A is generated by elements, then this idea of A to the T times the B to the S is equal to A times the this idea to A to the T minus 1. Sorry, it's R minus 1 and B to the S. Okay. The first and the second definition follows by the definition of the test idea. We prove the quality. And let's start with the right. And we take A to the T to the 1, B to S is equal to the sum of E, P, P, A, 1. Using our first lemma, we will write this idea of this part using the double sum. And we have that this is equal to the double sum A and B, A to B, And this is equal to the sum is equal A to infinity C in 1 and this is equal to the sum B that is equal to the test idea of A to R times B to the X to the X. So if A has a reduction by almost all elements, then we have the test idea of A to T is equal to A times the test idea to A to the T minus 1 for A T greater than R. Therefore, the set of jumping numbers that we denote by Jn of A is periodic with period 1. So now to describe the jumping numbers, to the jumping numbers, the interval 0, comma 1. Also, the set of example numbers is a final set.
You mean between 0 and 1? I mean between 0 and 1 is finite.
Yeah.
Okay.
Also, we have some properties that follows the properties of the test ideas. If A and B are ideal contained in R, we have the if A is contained in B, then the effective threshold of A is less than the effective threshold of B. For any integer positive, we have the effective threshold of A is equal to n times the effective threshold A to n. For now, if we have two ideas and we want to describe the best idea of the product, we have the next theorem that is named subjectivity. This theorem says if R is a ring, is a regular rectangle. A and B are ideas contained in R, and S and T are rational positive numbers. We have the test idea of the product the A to the T times B to the S is contained of the product of the test idea of A to the T and the test idea of B to the S.
When you say that the property of the jump numbers between the 0 and 1, you mean like the values of the jump numbers are in that set, or when
T is invisible. Okay. To prove the subjectivity theorem, we have tools of type closure. The type closure theory is something that I'm still learning, so I skip the proof. But we now discuss another application of the subactivity theorem that is about symbolic powers of an idea. We take an ideal A contained in R. The symbolic powers is denoted by A to N. This is equal to the A to the N times the W, the location W, R, where W is the complement of the union of the price associated of if A is a prime ideal, we have that the symbolic power of E is equal to N and the differentiation P and R. So we have that if R is a local ring, with residue field and A be any non-zero ideal, R and H is maximum case of any associated prime ideas of A, then A, this is the symbolic power of A to the H N is present in A to the H. For I layers bigger than one. Since R is a regular local ring, using the subadditivity theorem, the Scott theorem, we have the symbolic powers of H times N is contained in the test idea, the A to the H. We can rewrite the test idea. We have this N. The E over E. This is contained in the test idea. To the HN. To 1 over N, out of this to the E. So it's suffice to prove this.
The second one is actually equal to this, right?
Oh yeah.
Yes, yeah.
Thank you. Check that the test idea of A to H and to the 1 over N contained in the is contained in A to 1 that is equal to A. Maybe some localizing. Each associated friend of A since the localization on P has dimension as not T. And has infinite receiving every non-zero ideal of the localization has a reduction generated by numbers that each element. And two, that's since we have a to the h to n times the localization of p is equal to a to the hn the localization. So we have this idea of a to the h n is equal to this idea to a to h n p to the 1 over n, and this is equal to the text idea of a to h times rp, and this is contained in a to a times rp. So we conclude that a to hn is contained in a to h. This is for any integer.
Just one remark. I hope you appreciate how much of a ridiculous proof this is. Because the statement really has nothing to do with the proof. It's really this formalism of this idea so that you have this proof. And there is no other non-proof. It's fact. And also, by the way, it's implies that you solve the characters in zero. A reduction mark. So this gives you a proof of that statement in equal characteristic by an absolutely ridiculous proof first. It doesn't tell you why really, it's just testing. The crazy properties of them, so the activity is cut out. So these are very famous applications of this inverse operators.
Thank you. Okay. Also, we have the we can extend the definition of these ideas. For the product of ideas in so it says that if we have R is finite normal.
Perdón, es que está reservado el salón para las 12 y tenemos que poner una presentación.
No creo, porque este es nuestro salón de clase de siempre.
Pero siempre a las 12 ya podríamos usar porque estaba disponible todo el tiempo.
No, hasta las 2:20 tenemos nosotros.
A ver, ahorita le
O
preguntamos.
sea, porque este es mi salón de clase de siempre. O sea, de todos los
Sí.
demás.
Entonces hubo una confusión ahí, perdón.
Sí, me disculpo. A las 2:20 terminamos.
Okay. Normal domain. It is what guys spectrum of R. If we take ideals A, B1, B2, Bn, rational numbers 1, 2, is M. Then we can define this idea of A to the P times A V1 to S1 times V2 to S2 and so Bm to Sm. If you find it, smallest, no zero. Ideal, J, such that we have the same the definition of this ideal for A. That is P E to P minus 1, B1 to H1 to P minus 1, so on, Bn to Sn times Q minus 1. For R E positive and P in the form of R. Also, these test ideas share the same properties of the usual test idea. For example, we can rewrite that this idea like or First lemma. It says that this idea of T, B is 1, and B1 is M is equal to the double sum E P to the P to the C A T B E one is one B E and so on B M to S M B. Also, we have the solvability theorem. It says that this idea of AT, B1 is 1, and Bn 2 is M, is contained of the best idea of AT to the best idea to B1 is 1, times the best idea to Bn is N. And another properties also share the
Just to be clear, for that purpose,
I
you need not to be regular.
Yeah.
Just for selecting.
Okay, sorry.
In the usual case. I mean, as in the case that was stated before.
Yeah.
So we
Oh, you finished it?
yeah.
I thought you were about to say things about the constant regions and stuff like that.
I want, but I want to understand better.
Okay. Yeah, just to make a remark, it's just that when you try to understand how these ideals vary when you move the parameters T, S1, and Sm. So in the one-dimensional case, you're varying T in a line, and then you have these jumping numbers. But then if you have more parameters, you try to understand how that varies. So you're going to have the so-called constant regions. And the borders between the constant regions are going to be these P fractals. So they exhibit they are like fractals. So if you think about the two-dimensional case, in which you have two parameters, then you're going to have a first constant region where the test idea is just R. And then it's going to change. And that border is going to be some sort of fractal. In the one-dimensional case, you don't see it because it's a fractal, but it's just a point. So it's very boring. But in two-dimensional case, the border will be a line that is like a fractal. It's technically speaking, it's a P fractal.
Is there any paper with a picture of it?
A lot of them. Yeah, well, not a lot of them, but yeah. So what is the one we're looking at? So the first time I saw this sort of thing was in a paper by Felipe Perez, who is no longer in academia, but yeah, he worked out a few things about these constant regions. Daniel Hernandez, Pedro Teixeira, these are people who work on this and have some fractals. I remember one that is called the Machu Picchu fractal because it's in a three-dimensional origin space, and that's that's really a fractal. It seems like people are desperate to come to the so we can do that.